The next speaker here is the co-founder of Teardrop Security, which specializes in penetration testing and forensics. And this last year or so, he's been working really hard with the Metasploit project, and he's been developing some cool stuff, and he'd like to share it all with you. So without further ado, Egypt.
Thanks. All right, so as he said, I'm Egypt, and I'm going to be talking about Browser Autopwn. It's an auxiliary module for the Metasploit framework for fingerprinting clients trying to determine what browser is talking to your evil server, and furthermore, what operating system it's running on. And in so doing, we determine what exploits might work with that combination of operating system and browser. The first round of Browser Autopwn used to suck, and I'm hoping that it doesn't suck anymore. So here we go. I'm going to talk about some intro stuff, and then some of the techniques I use for figuring out what the clients are and what the operating systems they're running on. Go over some of the stealth options for trying to get away from AV and IDS, and a few demos. And I sacrificed to go to the demo gods last night, so I hope they'll work. Then we'll do a little short commercial comparison with MPAC and a couple of the other major well-known exploit packs for browser exploitation. As I said, I'm James Lee, also known as Egypt. I'm the co-founder of Teardrop Security, which is awesome. And I'm a developer for the Metasploit project, of which the Metasploit framework is the main product. I've been working with Metasploit for about a year and a half. I started submitting patches about 2 years ago, and as soon as HD gave me commit access, I broke the repository. So I got better. The Metasploit framework itself was created in 2003. I'm sure you've seen slides similar to these earlier today. It was rewritten in Ruby in 2005, and Ruby is so much better than Perl, and also Python. But it's more than just running exploits. Metasploit is a lot more of a framework, and it gives you a giant API for dealing with all of the sort of things that you would need to do when writing an exploit, protocols and whatnot. It also has modular payloads and encoders, so you don't have hard-coded shellcode up at the top of your exploit anymore. You see all of the old exploits, it's big chunks of hex at the top of your C file, and that doesn't scale. Metasploit gives us a way to make all of that easier. There's also a lot of non-exploit tools associated with the framework. There's stuff for making exploits, stuff for using exploits, stuff for writing exploits. There's traditional server-side exploits and client-sides, which is what we're talking about today. A lot of people have talked about why using client-side exploits is important recently. I won't get into that too much, but suffice it to say that if you can get in the middle, then a client exploit becomes huge. Or if you can get them to click on a link, then your client exploit is awesome. If you need any more explanations of this, talk to Chris Gates. He's awesome. And when building an exploit in Metasploit, there's a bunch of stuff for specifically HTTP. There's a way to build a heap spray in 2 lines of code. Now, that's a fairly complex technique. The idea is that you send giant chunks of shellcode with huge NOP sleds all over the heap, so that when you trigger some heap overflow or some heap corruption, it jumps into the middle of these giant NOP sleds, and you don't actually have to care about address space layout randomization and all of that stuff. We also have support for Sodorov's .NET DLL and his heap feng shui stuff, though that is a little more difficult to use. There's also a wide range of protocol level IDS evasion. So using HTTP itself to make it more difficult for an IDS to figure out what's going on a NIDS, and HTML evasions for making an AV have to work a lot harder to figure out what's going on. But the best part is you can write a simple exploit in 10 lines of code or less. And here's an example of that. I mean, might not mean much to you, but it's just a big chunk of HTML with a heap spray in the middle, and it triggers some vulnerable method. The send response method lets you create an HTTP response very easily. You just send it off and it works. Or it can be arbitrarily complex, and as an example, ANI load image chunk size, which is an old exploit, admittedly, is 581 lines of code. That's relatively huge. That's the biggest HTTP exploit we have at the moment. And as of June 28th, there were 85 browser exploits in the trunk. Those aren't all included in the 3.2 stable, but I'm not talking at all about 3.2 stable since so much has changed since that was released. There's also been several O-days come out for IE and a few others recently, so those aren't included in this number either. So a problem when exploiting a browser is you don't know what it is. You've got all of these options. We've got 85 exploits. Which one do we use? Is it running Java? Well, you can't tell when it first connects. So, and then you don't know what the browser is. So the solution for that, or my first solution, was a cluster bomb. And this is, for those of you playing at home, this is an MK44 Lazy Dog cluster bomb used in Vietnam. But the idea is that you know roughly where the target is, it connected to you. So you just send a whole bunch of crap at it and hope that it gives you a shell back. This worked fairly well for what it was doing, but it was initially very ad hoc and it was difficult to maintain. So we've moved on from that, and it was at the time it was basically, is it IE? Send all the IE exploits. So it was a huge pain in the ass when a new exploit came out. It was difficult to add to it because it was all one giant chunk of JavaScript. That's since changed considerably. Now it's very modular, and I'll talk more about how it is in that respect. Another problem when sending an exploit to a browser is one exploit might trigger some crash without giving you a shell, whereas another one could work. If you run the one that causes the crash first, then you never get to try the other one that might give you a shell. So the solution to that is a GBU paveway, also called a bunker buster, for using a guided approach, figure out what it actually is, send only the stuff that'll work. It doesn't make sense to send an exploit that'll only work in IE7 to IE6 or vice versa. And it really doesn't make sense to send Firefox exploits to either of them. And the purpose of that is to get around the possibility of a crash. And even worse, the client sees this crash or the browser hangs and they give up on you. Then not only do you not get your shell, they might call incident response and all kinds of bad stuff happens. It's much better to just get your shell and be done with it. So to do that, we fingerprint the client, figure out what they are. Traditionally, most of this has been done server side. So all of the main browser exploitation frameworks use the server. On the server, they use user agent parsing. It's unreliable because it's really easy to spoof. Several browsers have built-in capabilities of changing the user agent manually. You can also change it in a proxy. So several corporate web proxies modify the user agent before it goes out to the internet. So all of that stuff is harder to change in JavaScript. It's really easy to spoof it just on the wire, but in JavaScript, the JavaScript engine doesn't lie. And as sort of a step in that direction, there's a bunch of JavaScript objects that only exist in one browser. And a good example is window.opera. That's only available in Opera. That makes sense. Why would anybody else implement an object called Opera? But array.every only exists in Firefox. There's others, and a bunch of web developer people will be familiar with this. It's the idea for web developers is that they want to send a different style sheet or different JavaScript for each client so that their website works. Well, instead of making the website work, we're making the website give us a shell. There are other objects, JavaScript objects that only exist in certain versions of browsers. So in using that, we can get a fairly good idea of what the version is for any given browser. There's also some rendering differences and parser bugs that people use for websites for the same purpose, for sending the correct style sheet for Internet Explorer because it's broken. But those are less reliable, or well, they're very reliable, but they're less precise. So IE's conditional comments only work in IE, and all of like the CSS escaped comment bug only works in IE 5.5, and it doesn't work anywhere else. So those things are useful, but they're not very precise. However, Internet Explorer gives us a really awesome set of functions, the script engine family of functions. There's the script engine major version, script engine minor version, and script engine build version. And they're almost unique across all combinations of clients and OS. There's a few exceptions here. The combination of those three functions on 2003 Service Pack 2 and XP Service Pack 2 is the same, but otherwise it's almost completely unique. So using these three functions, we can very reliably determine that it is IE, what version of IE it is, and the operating system it's running on, including Service Pack. This particular technique was brought to my attention by Jerome Athias, and it was sort of the impetus for creating most of this framework. Opera gives us an even better solution. It tells us the actual version. There's a function called version, and it just gives it to you. And it's the minor version and everything. It's awesome. Firefox is a little bit harder. The only way to reliably tell what the version is by JavaScript object detection, like I talked about earlier. You know, array.every exists, then it's definitely Firefox, but we don't necessarily know what version. So we use some other JavaScript objects to figure out, say, for example, it's 3.0. But if the user agent says it's IE6, we know for certain that the user agent is lying. So don't trust anything about the user agent at that point. However, if what our object detection says jives with what the user agent says, then we can be fairly certain that it's not lying. And if it's not lying, it'll give us a more precise version information and more operating system information too. Safari is still sort of a work in progress. We don't have very many exploits for it. The ones that we do have are for older versions, mostly on iPhone, which is really cool, by the way, but it's a couple of years old, and so I haven't worked specifically with Safari for very long. The only thing that I've found, or the two things that I've found for sure identify Safari are the existence of window.console and window.onMouseWheel. Other browsers implement one or the other. So window.console is available on Firefox if the Firebug extension is installed. Not usually on any other browser, but that makes it not unique, and we can't use it reliably. But the window.onMouseWheel is only available in not Firefox. So Opera, Safari, and a couple of the other less well-known browsers have a window.onMouseWheel. But the existence of both of them assures us that it's Safari. Fingerprinting the OS is a little harder. Like I said, most of this traditionally has been done with the user agent, which again is unreliable, it's easily spoofed, and we don't want to send exploits for Linux to a Windows host. Doesn't make any sense. Another option would be to use something like P0F for passive detection of TCP artifacts, things that the TCP stack does on a particular operating system that look different. We don't do that because that's work. It's a lot easier to just ask the browser what it is. And again, Internet Explorer gives us these awesome functions, script engine, star version. All three of those guys give us a completely transparent view into what operating system it is. It gives us the user, it gives us the client, which it tells us that it's IE if they exist. It gives us the version based on what they are, and it gives us the operating system, including which version of Windows it is. Is it XP? Is it 2000? And the service pack. So these three functions are freaking awesome. Opera is a little bit harder. It's tougher nut to crack. It doesn't have a specific thing that'll give us a version, but it does have the opera.build number function, which gives us the platform. And that doesn't seem like much. It'll tell us that it's Windows, or it'll tell us that it's Linux. But that's enough to tell us that the user agent is or isn't lying. So we can look at the user agent, and if the user agent says it's Windows and it's 9.61, and our object detection tells us that it's Windows 9. And Opera 9.61, then we can be fairly confident that the rest of the operating system stuff in the user agent is going to be truthful. So using that, we can build a fairly reliable, though not 100%, detection for Opera on Windows or Linux or whatever. Firefox gives us this nifty little object called OS CPU. And again, it doesn't give us much version information, but it does give us a platform for sure. It'll always give us a platform, and this is independent of whatever the user agent says. So if you use user agent switcher, it'll change the values of navigator.user agent. Excuse me. It'll change the values of navigator.user agent, navigator.app name, and the other objects that people typically use for detection. But it doesn't change OS CPU. So this one little object can give us the Windows version through the same methods as we use in user agent detection, because it's the same string. So Windows NT 6.0 is Vista, I believe. Is that right? Vista. And from this, we use the same technique to go back through the user agent and determine whether or not it's lying. So others I haven't really looked at. Since we don't have anything specific for other browsers, all we've got is the user agent. So if our JavaScript detection doesn't find anything, then we just fall back to the standard server-side user agent detection, which is fairly reliable. If someone's not lying about it, then it'll work pretty well. And it's generic. It doesn't matter what the browser is. We're not looking for very specific things inside the browser to make this work. It just works because everybody sends a user agent. Sometimes they lie and we lose, but most of the time they're telling the truth. So right now I don't really do any fingerprinting of plugins or third-party applications. There are plans for making all of that happen, but right now I don't do it yet. QuickTime and Adobe are especially good targets for this because there are exploits for them all over the place. For other less well-known things that use ActiveX, we don't necessarily have to have a specific detection for that thing if we have an exploit for it. So to write an exploit for an ActiveX object, you have to have a class ID or a class name. And if that class ID or class name can be instantiated, then it's there. I mean, that if it exists, then then you can create it, or if you can create it, then it definitely exists. However, IE doesn't have a generic way of telling whether it worked. When you use a document.createElement object, this is supposed to create an ActiveX object. The problem is that it creates a DOM object that happens to implement all of the functions that the ActiveX object creates. So it always returns something that evaluates to true, so there's no way to tell if it actually got created or if it's just some DOM object. And document.write does exactly the same thing. If you create an object tag using document.write or document.body.innerHTML plus equals object tag, all of that stuff gets written out, but you get a DOM object instead of an ActiveX object. So there's no way to tell whether it really worked. However, if we know the name of a method, which we have to anyway for an exploit, then the type of that object dot the method name that you know will be something other than undefined. For ActiveX methods on an object, that's typically unknown. That's okay, as long as it's not undefined, then we know that creating the object worked. It might possibly be a real type, such as integer or string, if the thing that you're testing is a property. But either way, as long as it's not undefined, then we know that the object got created successfully, and we can go ahead and try an exploit against that object. So now we know what we've got. We've detected the browser. We've detected that this particular ActiveX object exists. Now what do we do with it? We've got to figure out what it's vulnerable to, or at least things that it might potentially be vulnerable to. And we do some of that on the server side. It's sort of a broad course determination, where first thing the client connects to our evil server. We send out the JavaScript to determine what kind of client it is, what operating system it's running on. We send all that data back to the server, and the server takes a look at it and examines it against various other tests that it knows. So the server knows that these exploits will work or potentially could work on Internet Explorer. So we weed out all of the other ones. We know this client is Internet Explorer, only send these exploits. Then a more fine-grained determination is made on the client. So with each of those exploits, we also send a test in JavaScript to check for the specific vulnerability. And I'm going to be picking on Mozilla Navigator Java here in a minute too, for most of this presentation. But if the Navigator.java enabled object exists, then we know Java is available on this box or on this client, and if we know that if we already know that it's Mozilla or that it's Firefox, then Mozilla Navigator Java is a good candidate to run against this client. So once we've picked all of those things, we have to select a missile, and this is especially fun. These are a whole bunch of Iranian and North Korean ballistic missiles. I especially like the No Dong. Yes, and at this point we also sort the exploits by reliability. So if we have an exe writer that just writes out a file and executes it for us, then we'll try all of those first, because they don't have any potential for crashing the browser. We want to try as hard as possible not to crash the browser until absolutely necessary. So we sort by reliability, send only things that are capable of working with that browser, and all of those tests are contained within the exploits themselves. So now, instead of browser autopwn having to know whether this exploit will work, the exploit itself can tell browser autopwn that it does. And we'll get into more of that later. So another problem is antivirus. And yeah, it really sucks when you get the user to click on your link and the user comes out and he connects up to your web server and he downloads your evil, and you send him off all these exploits, and then AV flags and you don't get your shell. That sucks. So the client might potentially be vulnerable to this thing, but if AV flags on it before it ever runs, then we don't win, and everybody wants to win. The solution to this is some stealth. So we take all of that stuff and wrap it up into something that doesn't look evil, even though it is. One of the ways we do that is obfuscation. So most of this stuff was originally written by Scape, but I've added some things and made the strings a lot more stealthy. So we randomize all sorts of identifiers, and we turn strings into things that become strings. So string.from char code, making hex strings that get decoded, using thing.chur, all sorts of ways of building a string that doesn't look like a string, so that instead of seeing the class name of some vulnerable ActiveX control, AV only sees a big blob of goo, and it doesn't know what to do with. So with luck, the only way that they're going to be able to figure that out is to implement most of a JavaScript engine to pull all of that out and recreate the string as it really will get evaluated as. And another part of this is using AJAX to go request more stuff from the server, eval a little bit of it, go request more stuff from the server, eval a little bit of it. And through that little bit of obfuscation too, we can make it harder for the AV guys and the IDS guys to figure out what's going on. But obfuscation is not crypto. And security through obscurity is no security at all. So we have encryption. It's not really encryption. It is, but we send the key along with the payload. So it's more like DRM than encryption. It's the same sort of problem. We have to get the key there somehow so that it can decrypt itself. But luckily, we can put the key in some place that most people don't look. If you put it in the URL, and then somebody goes and wgets your JavaScript looking for your evil, then they won't have the key when they run it through their sandbox because it doesn't come from the URL. And using this technique, a simple XOR is enough to beat everybody. Nobody can do this. I mean, a human would be able to beat it because it's just a simple XOR. So once you start looking for strings that might XOR into this thing, then it's really easy to figure it out. But that's not the kind of thing that a computer can know how to do on its own. It has to have help. And even better, if anybody does figure this out, it's trivial to just make the crypto stronger, make a bigger XOR key, make some extra junk that they have to do, make more hoops for them to have to jump through. And yeah, all of this just to get your shell. So, sort of blazed through that. Now we're going to try some demonstrations. And as I said, I did sacrifice a goat to the demo gods last night. I'm hoping this will work. So first thing, pardon me. So first thing, we've got, this is our resource script. It's pretty short and straight and to the point. We've got several actions in Browser Autopwn. The first of which is defang detection. That one is interesting because it doesn't do anything evil on its own. It just does all the detection. So, in fact, why don't we just run that on its own? MSF console takes a second. Okay. If we show actions, we see we've got web server, which is the main action that does all of the evil. We've got defang detection, which does none of the evil, but all of the detection. And it all goes into a database, as we'll see in a minute. And list, which is handy for telling us what exploits Browser Autopwn will run. We also have a debug, which prints more junk in the JavaScript. So if you're watching it in a browser, you can see all of the detection happen there. We have an exclude variable that lets us exclude exploits that we don't want to run. This is a regular expression, so it can be whatever you want. And match, which is the option of that, which is the opposite of that. It lets you pick only exploits that you want to run for this particular trial. And again, that's a regular expression, so you can make it as complex as you'd like. So since we're just listing, see, I'm matching on the word fire and Firefox escape rat val, the ODay that came out a couple of weeks ago, is the only thing that matches that name. We can set it to whatever we want. So dot will match any character. So now if we list, we get a whole bunch of them. And everybody likes more exploits. So that's just a list of the stuff that it knows about, and that list will be increasing soon. I'm working on more stuff for detecting Safari, and there are several exploits out in the wild that need to get ported to Metasploit. But as soon as that happens, they'll be ported into browser autoclone. So now we want to try the defanged detection. And that just creates one little server. So we can go over here, and you can see I'm running, this is Fedora, this is a virtual machine running Opera. So if we run that here, you can see it says I'm Opera 9.6.0. This is the user agent string. And this is all of the stuff that browser autopwn thinks it's actually running. And these undefined fields here are the operating system version and operating system service pack. Since Linux doesn't have a service pack, then that doesn't make any sense. And since this browser doesn't give us whether it's Fedora or Ubuntu or whatever, then that'll stay undefined for this browser. But for other browsers, we might be able to detect more. So, for example, Firefox gives us, well, okay, the demo got stuck. It gave us an undefined there, but either way, we still know that it's Linux and it's Firefox 3. We can also change, using the user agent switcher thing, we can change, now our user agent is an iPhone 3 user agent. We refresh this page. Now, you notice that our user agent is significantly different. Now it doesn't say anything at all about Firefox. It says it's Safari on iPhone, but all of our detection down here stayed the same. We know that it's still Linux, it's still Firefox, and it's still 3.0, and it's still on an x86 architecture. We can do the same thing in Windows. This is Firefox again. We see that it's Windows, it's XP, and Firefox 1.0 in this particular case. Firefox doesn't give us a way to pull out the service pack, but you don't really need it. However, IE is awesome. He gives us everything. We know the operating system, we know the version, we know the service pack, we know the language, we know the architecture, we know the browser, and we know the browser's version. And it doesn't matter if someone goes to all of the effort to go into the registry and change their user agent. I don't care. I detect it another way anyways. So all of that stuff will still work if someone takes that effort, which is considerable, by the way. You have to actually edit the registry and not screw it up and destroy your box. So that's all the detection stuff. We can see the options for browser autopwn are relatively straightforward. You have an L host, which is the thing for reverse connect payloads to talk back to you on. The serve host, which is the place where the server actually runs. And this can be 0.0.0.0 so that it listens on all interfaces. You can also specify a specific interface or a specific address and it'll listen only on that one interface. This is handy also to set your serve host to all zeros in the case that you're running the exploit running exploits elsewhere. So if you set up a gateway running exploits, you can have another instance of browser autopwn that'll catch all your shells in the same way that you would use a multi-handler. And the serve port is straightforward. That's just the port that we listen on. SSL says whether or not to act as an SSL server. HD broke this recently, so I'm not going to test it. And URI path is just the place where the browser will request, or you want the browser to request when it talks to your server. And usually I just use /, which means the root, which is the default thing that browsers try when they connect to a server. If they don't have a path to look for, they'll just try slash. So I usually just use slash in the URI path. You can set it to whatever you want, but then you have to get a user to click on something with that path in it and all of the associated troubles. So now, and we saw the debug, the exclude, and the match. We can set debug to false so we don't print anything for the user to see. And I didn't change the action. Okay, so you can see here it's picking all the exploits and setting them to random paths. If you set debug to true here, the paths won't be random, they'll be the name of the exploit, which is handy for determining which exploit is going to run on a particular client, but not the kind of thing you want an actual user to see. So turn off debug if you send this to somebody. So now we've got that all set up. We go back to our virtual machines here. See Opera on Linux. Hey, that looks like fun. And we got a command shell. And I'm running as user vulnerable. So that's pretty straightforward. Oh. Stop it. So without changing anything on the server, we also go over here to Windows on IE, or IE on Windows. And we have a JavaScript error. Awesome, thank you, demo gods. Okay, I promise it worked yesterday. Okay, so, oh, I forgot to talk about databases. All of this stuff can go into a database too. Now that we're connected to a database, run the same exploit again. And now we can see we had a connection. We know the OS, it's Linux. We can get more information about it. We know it made a request for slash, and this was its user agent. We get all the same stuff from IE, which apparently now is going to give me a shell. Awesome. Yay! Everybody loves shells. So now we can background that guy. And more DB hosts, except, oh, I'm using VirtualBox, and I haven't used VirtualBox for very long, and I just ran into some quirks. Apparently all of the internal addressing comes from 127.0.0.1, so my database thinks all of this is one client, it's one host. VirtualBox is kind of dumb. Anyway, but we can see that it was Windows XP, and that we can get some more information about it. It made another request. It was MSIE 6.0. So, let's see. I think that's all my demos. Go back to the fun stuff. How's my time? Come on. Yes. Okay, well, maybe those virtual machines just ate all of OpenOffice's memory. Let's see if we can do this. You can do it. Come on. That's a good little virtual machine. Maybe? Oh, come on. There we go. Okay. So I hope that worked. Most of it did. And now that we've seen what it can do, how do you make it work for you? That's what all of this is about, is making it easier to write exploits. Not just using them, but writing them and having fun with them. Writing new stuff for browser autopwn is really no harder than writing the exploit itself. It's basically you add one little function call up to the top of your class called autopwn info. And in there you put more stuff about what this exploit does. The vulnerability test that you can run when it sends for the JavaScript. And this is different in ActiveX because, as I said, there's no easy way to test for the existence of an ActiveX object, so we set up a special way of dealing with ActiveX. But all of the information that you need for writing the vuln test and the rest of the autopwn info comes directly from the exploit anyway. It's all stuff that you already have to know to be able to exploit it. And here's an example that I picked on earlier, is Mozilla Navigator Java, and I think you can probably read that, but you can see it's not a whole lot of extra code. You're just passing in, this is a constant describing what the browser is. It requires JavaScript. Some exploits that don't require JavaScript get sent in case JavaScript is turned off. So if you can do the exploit without JavaScript, then setting this to false will work on hosts that have JavaScript turned off. We also use a ranking system for determining when to send this particular exploit. This is ranked exactly in the same way as payloads are ranked for compatibility with exploits. And so there's a manual ranking, which means don't run this unless I tell you to explicitly. And then there's a low ranking saying this one doesn't work all the time. There's a normal ranking, and there's an excellent ranking, and a few others. But for normal, I've sort of arbitrarily decided that reliable memory corruption bugs ought to be normal ranking, because they almost always crash the browser. So you want to try them last if you can run something else that won't crash the browser first. But interesting here, I think, is the vuln test. It's really quite straightforward. It's just a simple little chunk of JavaScript. It's not a whole lot of code here. We're just testing for the existence of an object required to run this exploit. And we set one variable to true, saying that this client is vulnerable to this exploit. I think it's relatively easy to set all this stuff up. And here's an example for an ActiveX object. 06067 is the venerable and awesome first published heap feng shui exploit, which is totally awesome. And if you love exploitation technology, you should absolutely be reading the source code for this exploit. It's awesome. But it uses a class name, directAnimation.pathControl, and the vulnerable function is called keyframe. So we just set that into our vuln test instead of having the JavaScript for it in this place. And you can see how that's different from the WinZip file view vulnerability that Dean DeBeer wrote and dropped a couple of months ago. Instead of having a class ID, or instead of having a class name, you have the actual class ID here. But otherwise, it's exactly the same. You can see the difference is minute. It's just those two little things. There we go. So now we've sort of seen what browser autopwn can do. It's got reliable target acquisition. It determines what the browser is. It determines what operating system it's running on, picks exploits based on that. That's the smart missile selection. You don't want to send, you don't want to send a GBU paveway at a guy. It's overkill. You don't want to send a cluster bomb at a bunker because it's just not going to work. So you got to have some smart detection to have smart exploit selection. And from an AV perspective, this is pretty hard to detect. The the encryption and obfuscation make it so that the antivirus guys basically have to have a JavaScript engine for this to, they have to go through all of the same stuff that a browser would do to set up the exploit in exactly the same way. And if there's anything different there, they're going to false on stuff or they're going to miss things. Another important point is the browser autopwn is easy to extend. If you want new exploits, you just write them for the framework exactly like you would before. New browser exploits are relatively easy to write in the framework. Mario can attest to that with all of his ODay. But it's relatively easy to write exploits for the framework, and writing exploits for browser autopwn is really no harder than that. And all of the stuff that you learn from running an exploit and from having a client connect to your evil server is stored in a database. And I don't currently now do anything with statistics on that, but it conceivably would be pretty easy to take all of that information, put it up on some kind of pretty pie chart and show your boss, hey, all of these people clicked our stuff, and these are all of the shells I got, and you need to hire more security people. So now I'm going to talk about some of the other exploitation packs that are out there. In general, they're good for what they're made for, but I think they suck compared to browser autopwn. And the Russian Mafia may kill me for saying that, but MPAC and Firepack are sort of the big players, some of the first exploitation packs that came out on the market. Neosploit and LuckySploit are relative newcomers in the field, and they're fairly advanced. Neosploit and LuckySploit are pretty hardcore, whereas MPAC and Firepack, since they were the early guys in the field, they don't have as many advanced features, but we'll talk about that later. One of the biggest downsides to all of these other exploitation frameworks is that they're hard to get. The legitimate way of getting MPAC and Firepack is to send $4,000 to some guy in Russia, and I don't know about you, that doesn't sound like a good idea to me. Or you can pull it off of a compromised web server where somebody has deployed these evil packs. But there's downsides there too. Is it backdoored? Who knows? You have to go through every line of source code to check it out, and they're doing some of the same sort of obfuscation techniques to get around people stealing their exploits. And all of those exploits are going to be old. If you pull it off of a compromised web server, then who knows how long it's been sitting there? And are these exploits usable? Do they only work in certain versions? Have they been tested? Who knows? Additionally, all of their detection is server-side. Everything is done through the user agent. So if a proxy is modifying a user agent on the fly, this stuff won't detect that, and you won't get your shell. It's also hard to change or update the exploits. If you get a new exploit, it's really hard to write it in PHP and go through the, hard code some shell code up at the top, and do all of the stuff that you used to have to do in 2001 to write an exploit, when all of that stuff has already been done for you in Metasploit. The obfuscation they use is XOR, so it's very similar to what Metasploit uses, but they don't separate the key from the actual JavaScript itself. So they don't put it in a URL or some other place that it's difficult to get. Now, Neosploit is a funny one. It's compiled elfs that run as a CGI, and the only copy I've gotten a hold of Neosploit is for FreeBSD, and so it's FreeBSD elfs running as a CGI, and I don't really want to do a whole bunch of reverse engineering to find out what the shellcode is it uses, and I just want to run my exploits and I want to get my shells. I don't want to go through all the effort of figuring out whether my exploit framework is going to send all my shells back to Russia. That's not part of the fun. So you don't really know what this thing is doing unless you do some hardcore reverse engineering or somehow get a hold of the source code, which I haven't been able to do in a couple of months of trying. LuckySploit is different altogether. It uses real crypto. It's actually RSA and RC4 implemented in JavaScript. These guys are hardcore. I don't do that because one, holy crap, and two, I don't think it's really necessary. I mean, yeah, it's hardcore. It's like, that's some serious stuff, but AV doesn't see it anyway, so who cares? Why go to all that trouble? But it's really hard to get lucky exploit too, and it's the same problem as with all of the other guys. It's difficult to get it, and once you got it, do you know if it's been backdoored? Who knows? Yeah, I mean, you have to go through every line of code to check, and that's not fun. So in contrast, browser autopwn is really easy to write new exploits for. It's easy to take out old ones. There's a little variable you set called exclude, and it'll take out all of those exploits and not run them. So if you don't want to run something that you've found to be unreliable, then just don't run it. It's easy. It's really easy to get. You just go to metasploit.com and download it. And once you've got it, it's free. You can do whatever you want with it. You can modify it. You can sell it if you want. But if you do modify it, I'd like it if you send me back some patches, and so we can all benefit from it and make it awesome. One of the biggest upsides to browser autopwn is it's not written in PHP. Freaking hate PHP. And all of the OS and client detection is done client side, so it's a lot more reliable. Well, most of the detection is done client side. We still fall back for a few things, and we, as I said, we use the we use the user agent when we can determine that it's probably not lying. So in those cases, I think it's an acceptable risk. If somebody is spoofing it just a little bit, it's probably close enough, and our exploits might still work. So all of this stuff will work in the presence of a spoofed or a broken user agent string. Some third-party tools modify the user agent string in Internet Explorer and completely break it. Like they'll change a little section and take out a parenthesis, and which totally destroys the rest of the user agent, and all your parsers don't work. So now you've seen all of that stuff. What now? Well, I'd like some more flexible payload selection. Right now, that's basically, if it's Windows, use Meterpreter. If it's not, or if we can't tell, use a regular shell. That is kind of a downside for exploits that might work on Windows. So for example, Mozilla Navigator Java works on Windows and on Linux, and on Mac, but we don't have an easy way of making that be a Meterpreter shell on Windows or a command shell on other things. So that's kind of a downside, but we're working on that with the generic payloads. It's sort of a Metasploit problem more than a browser autopwn problem at this point, but we're working on it. I'd also like to stop when you get a shell. This could potentially be really hard. If for example, a proxy is in the way, and all your clients are connecting to you through this proxy, then are they all one client? I don't know. If it gives me a shell, which one was it? I don't know. And the same thing with that. If everybody is coming from the same IP address, how do you tell which one of them gave you a shell back? One of the possible ways of dealing with that is to just run a Meterpreter script. As soon as somebody gives you a shell, you run a Meterpreter script, find out what their internal stuff looks like, and use that compared to your database of who you sent exploits to. But that won't work on a regular shell. That won't work on a command shell. Another possibility is changing all of the exploits to a download exec and hosting the payload through browser autopwn in addition to having the regular reverse connect. I don't like that nearly as much because now it means we're writing something to the disk instead of just using Meterpreter in its full awesome glory. So those are some difficulties with dealing with that particular problem, but I'm hoping to come up with a solution, and if you can think of anything, let me know. I'd also like the JavaScript obfuscation to be a little easier to use. Right now you have to determine at time of code writing what the variable names are that you want to be obfuscated, that you want to change. That's kind of a pain. I'd really like that to be automatic, but that basically means writing a JavaScript compiler, and that sucks. I don't know if I want to go that far. So XOR might actually replace all of that anyway. If we can just XOR everything and then you don't have any identifiers, then who cares if the identifiers aren't obfuscated? It's all in an XOR anyway. Another possibility for detection is UAPROF for mobile devices. That's the User Agent Profiler standard, and it's not really all together yet, but a bunch of people are trying to make mobile devices conform to a specific standard that says, this is what I'm running on, these are the capabilities that my phone has, these are the plugins and the file types that I can deal with. And that's a whole crap load of information. I mean, if it tells us I'm running on a Java phone and I can read QuickTime movies and I can do these kinds of things, that gives us all kinds of stuff as a starting point for what exploits might work. If it tells us it runs QuickTime, well, hey, throw some QuickTime exploits at it. And all of that would be really useful. The downside is it only works on mobile devices. It'd be great if we could get Internet Explorer to do that everywhere. Say, yes, I have all of these plugins, there are all these versions, and oh, by the way, here's your shell. And lastly, I'd really like to integrate this with Metafish. Yeah, this is the stuff that Val Smith and Colin and Dave Kerb have been putting together. It's freaking awesome. Sending a whole bunch of evil email, getting people to click your links. I would really like that to all mesh in with Browser Autopwn and having a full, complete phishing framework from sending the email to getting the shell and everything between. I think that would be freaking awesome. Of course, that's going to take some time. I don't know how much time, but it's definitely a goal for the future. You can download it from Metasploit.com. You'll have to check out the Subversion copy, which I tend to break on a regular basis these days. I don't know what's going on there. The 3.2 version of Browser Autopwn, the one in the 3.2 stable, is kind of crappy, so I'd stay away from that one. Use this one. And if you find a way to make it more awesome than it is now, send me a patch. I want to make it awesome for everybody. So, these are all the people that helped, especially the guy who made ActiveX. I'd really like to meet that guy, actually. Like, the guy who sat down at a boardroom someplace and at a boardroom conference table and said, we've got this browser, and it can read XML, it can read HTML, it can read all of these file formats, it can do all of this stuff. It's got a JavaScript engine, so we can get stuff from the user and run it. That's awesome. But we don't have enough attack surface. So, yeah, any questions? It was so awesome that there are no questions. All right. Okay, well, I guess we're quite a few minutes early. Okay, well, there's a question.
Have you looked at Listo PDS or Sutra apps, which are craft shapers that sit in front of web export apps?
So the question was whether I've used Calypso, and what was the other one's name? Sutra. Things that sit in front of web exploitation frameworks. No, I have not. I'd like to hear some more information about that if you've got it. Yeah. Okay. Well, if there are no other questions, I've actually got like 15 minutes left. Thank you. So yeah, since I've got about 15 minutes left, I have another presentation that I was going to give, but then ended up not being on the schedule for. So if you're interested in PHP payloads, I could talk about that for another 15 minutes. Yes? Okay, so I'm just going to skip this stuff. PHP gives us a ton of ways of running system commands. There's a dozen different functions that let you do it. You've got system exec, shell exec, pass through, proc open, p open, p control open, and a few non-default extensions. There's a Perl extension for PHP. I mean, come on, you can run Perl inside PHP. So you've disabled all this stuff. You've turned off all of the system commands. So all of those are disabled, and you've set up safe mode so that no one can write outside of your web root and all of that stuff. And then you give me Perl. Okay, I'll just run system from there. Shut up. Opening sockets is pretty easy in PHP too, because there's a whole bunch of functions to do it. This is the biggest downside of PHP, because there's it's a crappy implementation of a crappy idea where they said, okay, we need all these functions. Oh, but I forgot we already implemented that. We'll just give it a different name. So socket, fsock open, pfsock open, all do exactly the same thing. They open a TCP socket. What's even better is they can take URL wrappers and put all of that stuff in fopen and other crazy places. And if we can run system commands, then we can just do sockets through something else. So if sockets aren't compiled in, then you could just use Perl again, or you could use Bash with dev TCP. That won't work on Debian-based distros, but you still got Perl, so who cares? The coolest thing is that you can reuse Apache sockets. They don't set the fd cloexec flag on their file descriptors, so you can read any of their read file descriptors, write any of their write file descriptors straight to Apache. So you can read or you can write to their logs, which I think is hilarious. But you can also use the same thing for their socket, so that you connect up to the server, you request this page, and then you start typing commands and it works. It's freaking cool. So there are some existing payloads for PHP. Well, there's actually a ton of existing payloads for PHP. Two of the biggest are C99 and R57. They both suck in their own different ways. R57 is especially evil because it's got this big chunk of base64 crap down at the bottom. What that actually does, if you decode it, is it calls out to Russia and sends all your shells to Russia. Like, thanks, guys. There's tons of private shells. Most of them are really simple because it's really easy to write a shell in PHP. So everybody's done it, but mine are cooler. So since there's all of these others, why bother? They're mostly built for owning websites and databases, not owning networks. And I'm much more interested in owning networks. And like I said, many of them contain backdoors that send shells back to Russia or China or wherever. These are the Metasploit payloads that I've built recently. Missing from this list is download exec, which I committed and broke the repository with a couple of days ago. Exec does what it sounds like. It execs a system command. Bind PHP binds a shell to a server port. Reverse PHP calls back and gives you a shell. And shell findsock is the one that works on Apache, like I said a minute ago. So you can use Echo to get a shell from Apache. I think that's so cool. And coming soon to a theater near you is PHP Interpreter. This is going to be freaking cool if I ever get it together. There are some difficulties in PHP because its select calls are crap. There's two different kinds of file descriptors in PHP. There's socket file or stream file descriptors like socket creates, and then there's file descriptors like fopen creates. And they can both be sockets, but they don't work with the same select call. There's stream select and there's select, and they don't work together. So you have to do some timeout magic to make all that stuff happen. Anyway, that's where I am now with PHP Interpreter. It's coming soon, I hope. Bind is really easy. There's a function called socket create listen, and you just run that function. If that function doesn't exist, then you do the standard create bind listen. But the downside to bind is that it's not a real shell. Reverse has the same problem. They're not a real shell. They're just a collection of things that run system commands. So you send a command, it creates a new shell, runs that command, gives you the output. The downside of that is that CD doesn't work, so you can't change directory. Otherwise, it's just like having a regular shell. Findsock only works on Apache on Unix-like systems because they don't set the cloexec flag. I still think it's totally awesome that you can write to their log files. But yeah, this is a real shell because we're actually using bash to take over the file descriptors and send all your stuff through bash. Totally awesome. And this is what it looks like. You echo all the stuff necessary to request the page, and then you start typing, and it gives you a shell. I love it. There are problems with writing PHP payloads. The first is disabled functions. In the php.ini, there's a command or a directive called disable_functions, and that basically turns those functions off, and they'll never work. But you can test for them with the isCallable function. You say isCallable, then some function name, and through that you can determine whether this guy is going to work. And if it's not, well, we can just try one of those dozen other functions that do exactly the same thing because PHP is stupid. Then there's also character filtering. Most PHP exploits are either a file include or an eval bug. Occasionally you get file uploads. But those are subject to character restrictions. You might not be able to use, so for example, a quote is really commonly filtered out, really commonly filtered out because of the magic quotes GPC. It turns all your quotes into backslash quotes, and that's no fun. I want my shell. I don't want to deal with quotes. SSL is a problem now too because HD broke it. With the new interpreter, everything is wrapped in SSL. PHP can't really do that, at least not that I can tell, which means I might have to actually implement most of SSL in PHP, and I'm not looking forward to that. Disabled functions, like I said, you can just try all the other ones. There's a bunch of them, so just try other functions until one works. Filtering, you don't really need quotes when it comes down to it. PHP parses things as, yeah, magic quotes right here. PHP parses bare words first as a constant and then as a string. So if it's not a constant, then it tries to parse it as a string. So we can use just a big chunk of base 64 and say, here's my string. And since there's no quotes around it, treat it as a constant. Oh, well, there's no constant called B12.8CQ, blah. So then it'll try it as a string, and then we can base 64 decode it, and we win. It does have a 998 character limit. I'm assuming this is something to do with PHP's identifiers, or how it parses its identifiers. It only has like 1,000 characters for an identifier, and a constant counts as an identifier. So that, at least that's my postulate. I don't know if that's actually the case, but it's really easy to just chunk it up into smaller pieces and continue on, just concatenate everything together. So I just put everything in base 64, convert the things that can't be used as a string, so plus and slash, into things that become plus and slash. And all of this magic comes together and creates about a third, again, the size of your payload. But it's PHP, so who cares? Who cares if it's big? I mean, we're sending a file anyway, right? And like I said, HD added SSL support to Meterpreter, which completely broke all of this stuff. It made Meterpreter better, though. Meterpreter is awesome. Now everything's encrypted. I just don't want to have to implement in PHP. So Meterpreter is still a work in progress. It's mostly there, although the core stuff works. You can execute a process, you can download a file, you can get a process list or a directory listing, but all of the channel stuff is broken. So when you execute that process, you can't see what it did unless you write it to a file and download the file. It's kind of a pain. So you also don't have process interaction. You can't have a shell, an actual shell using this. And there's no pivoting, which is a bummer. It was sort of the point of creating Meterpreter so that you can pivot through a web server to something behind it. But to do that, I need to get all the channel stuff working. That's still in the future. Apparently I have this slide again. And I'm not doing demos because I don't have time. Questions? No questions? All right. Well, I'm willing to break early now.